Hi everyone, welcome back to Chem Story. Today we're looking at a unique kind of alkene reaction. It's called the radical addition of HBr, and it works a little differently from what you've seen before. The key twist here, it only happens in the presence of peroxides, and that changes everything. So what exactly is this peroxide effect, and why does it matter? Let's take a closer look. All right, let's start with the big picture. Normally when you add HBr to an alkene, it follows Markovnikov's rule. That means the bromine attaches to the more substituted carbon, the one with more alkyl groups around it. But if the reaction takes place in the presence of peroxides, things change. Now it follows a radical mechanism, and the product is completely flipped. This time, the bromine ends up on the less substituted carbon, and that's what we call an anti-Markovnikov product. We'll dig into how that happens in just a minute. But for now, just keep this in mind. When you add HBr with a peroxide, the usual rule gets reversed. Let's walk through the mechanism. Starting with step 1, initiation. We start with the peroxide, written as ROOR. When you apply heat or light, that central bond breaks and you get two alkoxy radicals. These radicals are highly reactive. They quickly attack HBr, pulling off a hydrogen atom to form ROH. And in the process, they generate a bromine radical. And that bromine radical is what gets the radical chain reaction started. So initiation is all about creating bromine radical, which sets everything else in motion. Now let's move on to step 2, propagation. This is where the actual product starts to form. First, the bromine radical adds to the alkene, but it doesn't just add anywhere. It attaches to the less substituted carbon of the double bond. Why? Because that leaves the more substituted carbon as a radical, and that's more stable, thanks to hyperconjugation and alkyl group donation. Then that carbon radical reacts with another HBr molecule. It grabs a hydrogen atom, forming the final product, and at the same time regenerates a new bromine radical. So the cycle keeps going. Bromine radical is used, then remade again and again. And that's what makes this a radical chain reaction. In the end, what do we get? An anti-Markovnikov product, all because of this radical pathway. Let's wrap up the mechanism with step 3, termination. At some point, the radical chain has to stop. And that happens when two radicals meet and react, canceling each other out. One common case is when two bromine radicals combine to form Br2. No more reactive species. So the chain stops there. Another possibility? A carbon radical might bump into a bromine radical. If that happens, they form a stable bond, and that completes the product. Either way, termination brings the radical process to a close. So why does this reaction give us an anti-Markovnikov product? It all comes down to the stability of the intermediate. In a radical mechanism, we're forming a carbon radical, and that step needs to be favorable. When the bromine radical adds to the less substituted carbon, it leaves the more substituted carbon as the radical, which is more stable. Why is that? Because of hyperconjugation and electron donation from nearby alkyl groups. That extra stabilization makes this pathway more favorable. So it's not random. The regioselectivity is driven by radical stability. And that's exactly why we get the opposite product compared to the ionic version of HBr addition. Now, what about stereochemistry? Well, here's the thing. This reaction is not stereoselective. In the first propagation step, the bromine radical can approach the alkene from either face, top, or bottom. And in the second step, the carbon radical that forms is planar, so HBr can also attack from either direction along the p orbital. So in the end, you get a mixture of syn and anti-addition products, and they form in roughly equal amounts. In other words, there's no strong preference. Both outcomes are equally likely. And that's pretty common for radical mechanisms, since the intermediates are usually flat and symmetric. Here's a quick visual summary of what we just talked about. In propagation step 1, the bromine radical adds to the alkene, and it can do so from either face. That gives us a planar carbon radical. Then in step 2, HBr approaches the radical, again, from either the top or the bottom. And that's why we get a mix. Some products where the two groups are added to the same side, that's syn, and others where they end up on opposite sides, that's anti. This kind of diagram helps make it clear why both stereoisomers are formed and why the reaction isn't stereoselective. Before we wrap up, there's one more important point to mention. This peroxide effect only works with HBr. If you try the same reaction using HCl or HI, the radical mechanism doesn't go through. Why not? Because in those cases, one of the propagation steps is too endothermic. It requires energy input, and that makes the reaction energetically unfavorable. So even if radicals do form, the chain reaction doesn't keep going efficiently. Without a smooth and favorable energy flow, the mechanism stalls, and the reaction just doesn't proceed like it does with HBr. Alright, that brings us to the end of our lesson on the radical addition of HBr to alkenes. We looked at how peroxides reverse the usual regiochemistry, how the radical mechanism works step by step, and why the reaction is regioselective, but not stereoselective. Just remember, this only works with HBr, and it's all thanks to the unique nature of the radical chain process. Thanks so much for watching, and I'll see you in the next Chem Story video.